BSides DC 2016 videos are brought to you by clearedjobs.net and cybersecjobs.com, tools for your next career move, and Antietam Technologies, focusing on advanced cyber detection, analysis, and mitigation.
I was going to say good afternoon, but no. Good afternoon, BSides. Thanks for having me here. My name is David Bianco. I'm here with my friend Chris McCubbin. We both work for a vendor called Squirrel, but we're not really talking about Squirrel today. I want to talk instead about something that, well, Chris is our real expert here with machine learning. I, as a security analyst, have been getting more and more into being able to incorporate machine learning kind of tools in my daily work. And I felt like we're getting now to the point where you don't really have to be a machine learning expert to get some value out of machine learning to do common security tasks. So I wanted to put together a talk, and Chris and I collaborated on this, and the central thesis of our talk is it is now perfectly feasible and perhaps even time for most of the people in this room to be able to go back to their office tomorrow, find some intractable big data problems that they've been having, and have the possibility of pulling out a new tool out of your toolbox, some simple machine learning. And so that's what we're going to talk about today. We have a demonstration program. It's on GitHub. I'll show you the URL for that later, where you can actually see some of the Git machine learning code examples in Python. We're not going to talk a lot about the Python piece today. Instead, we're going to talk a little bit more about the ideas behind machine learning so you can make some intelligent choices. So, show of hands, who in here has ever heard this piece of advice, that it's a best practice to do log review every day or every week? I'm disappointed. There's only like 5 or 6 people. Maybe that means that everyone has just banished this from their minds. This is no longer like a feasible thing to do, right? If this was the Family Feud, it would be like, survey says no. This is not really considered a best practice anymore. Although when I started in security, it definitely was a long time ago. It considered something that you could actually review all your syslogs. Like a system administrator could sit down there and read their syslogs, maybe with a little help from grep or something like that to format things. But that's really no longer the case. Even a small or medium-sized business can potentially generate gigabytes of log files every day. When you get to an enterprise level, you are probably at least at terabytes, if you're not higher. So the problem is that kind of these things, we're so good at logging now, which is really a good thing, right? For us, visibility is always good, but it brings this problem with us that we are no longer operating at a purely human scale. My take on this is that is okay, because now we are at the point where we have the humans, like us, right? We're really good at understanding context, be it business logic that goes along with some process, or maybe it would be some intelligence that we've read, or even the idea of, I know how this type of system is supposed to work. Like, I know in general how an email server works. This looks weird. We're really good at that. We're so good at that sometimes we can find patterns where there are really no patterns. Like we find Elvis on toast. And he's not really hanging out on your Wonder Bread, unless you put some peanut butter and bananas maybe on it. Then he might be there. But our brain is wired for patterns, and we see that. But that's a rare false positive. We can make use of our pattern ability by combining it with some of the things that the computers are good at. That is repetition, going through large volumes of data, applying an algorithm kind of tirelessly, doing the same things over and over again. And when you put those two together, you have what I think of as kind of like the closest real world example of cyborgism that I can come up with. A cyborg being a part human, part machine. Well, that's the title of this talk, right? Practical cyborgism. It is now practical to combine the human and the computer with your big data security problems. I just hit all the buzzwords. Sorry. Yeah. To get some practical, useful analytics out of it. So here's a problem statement that you can't read because our projector is not really good enough to read our slide, but it's basically a bunch of small type bro HTTP logs. Just big wall of text. You don't really have to read it just to know that your logs are a big wall of text. And even if I show you just one screenful at a time, there's no possible value that you could get out of that without staring at it for like 5 or 10 minutes. And if you think of at the scale of data that your organizations are collecting, do you really have 5 or 10 minutes to stare at each screenful? No, not really. So Chris and I have come up with a I don't want to call it a solution really to this project, but I would like to say it's a prototype, like proof of concept solution for this kind of problem, cutting through all the logs to get to the things that we are interested in. We call it ClearCut, and it's available on GitHub. It's written in Python with some standard Python machine learning libraries as an example that you'll be able to go to after the talk and see how we did it. We don't necessarily think that you're going to immediately go out and use this into production use, but you could definitely give it a try. But the idea of it is it's a functional proof of concept that you might learn from or extend to your own kind of logs that you have in your environment. We work with bro HTTP logs in this proof of concept, but you could, and we provide pointers for guidance on how to extend it to your own kind of logs that you have in your environment. So at this point, I'm going to turn it over here to Chris for a few minutes, and he's going to talk to you a little bit about some of the concepts of machine learning. And then after that, I will come back up and talk to you a little bit more about ClearCut itself. We'll do a little screenshot demo, and I'll talk to you about how to interpret some of the outputs of the machine learning process, and then we'll do a wrap-up.
Try to turn this on without too much feedback here. Thanks, David. So yeah, I'll talk. Well, it's really loud here. I'll talk for a few minutes about. Let me move this over. Some of the important concepts in machine learning. How come yours works so well? Mine's like weird. All right. So we'll start out here with a little analogy. So I'm going to claim that good theory leads to good programs. You know, it's kind of like the whole idea of computer science. The discipline is that you want to come up with good theories, and those lead to good solutions to real-world problems. So who here has implemented and optimized non-deterministic finite state automata compiler? I mean, maybe I did it in school. I don't really remember. But you probably use one every day. So who here has used grep or Perl regex, right? Everybody. Well, what you're really doing there is you're running a compiler for your non-deterministic finite state automata, right? So you're really making one of those. But you don't care. You don't care that it's NTM inside. You might need to know a little bit about its quirks. Like, for example, actually grep and Perl and everything that's based on Perl regex are implemented quite differently, right? Like, so grep is based on, it's based on a sort of a compiler that's more efficient, and it doesn't do backtracking, right? So grep doesn't have any bad cases. You can't make grep blow up on various regexes. Perl does do backtracking, and because of that, you can write regexes that make Perl go exponential, essentially, in its running time, even on very, very simple strings like A star, AA star star, something like that. So, it's helpful to know this. You don't really have to know why. You don't have to know the theory why, but you might want to know that, yeah, sometimes Perl blows up on regexes. So, as kind of an analogy here, like, you don't have to know, the intricacies of, say, like random forests to use random forests, right? Or to use machine learning in general. And, but it might help to know that sometimes these things blow up or what they're good at. So machine learning has like a long storied history. I mean, it goes way back to the huge names like Alan Turing. He invented things like the Turing test. It's intertwined with artificial intelligence, statistics. You could have a whole talk on the history of machine learning or the history of AI, machine learning, statistics, data science. I'm not going to talk about that much here. But basically, there's two, and even two is kind of oversimplification, but there's two big branches of machine learning that we're going to talk about today. One is supervised, the other is unsupervised, and they do different things, right? So supervised learning is, so you might have, you need labeled training data. That's kind of the big thing. You need examples to show the machine to help it learn. And given those examples, it will try to figure out patterns in your examples that it can apply to unlabeled data to try to label that data. So you have a bunch of pictures of cats and dogs, and some of them are labeled cat, and some are labeled dog, and you pass it to the machine, and then you show it a picture, and it says, I think it's a cat, and maybe it's right. If it's right, that's a true positive. If it's wrong, that's either a false positive or false negative. Sometimes you'll hear these terms, but is a cat positive? And I guess it depends if you're a cat person. But it's usually you have a positive class and a negative class, or a true class and a false class. So a true positive will be something that's right about, that's a positive, and a false positive will be something that it says is positive, but it's not. So the other big area that we're going to talk about is unsupervised learning. So this is, I have no idea what's in my data. I have a bunch of, keeping with the pictures example, I have, a million pictures. I don't know what's in them. I don't know if it's cats or dogs, aardvarks, clouds, whatever. So I'm just going to give this to the machine. The machine is going to look at this data and come up with some of its own conclusions. It's going to come up with some of its own groups that it thinks that these things are part of, or it's going to come up with what it thinks is normal. And then when you pass it a new picture, it's going to tell you, oh, I think this is group 2. Well, group 2 might be cats, but the computer doesn't know that. All the computer knows is, I learned about all these things in the pictures, and I think this group looks like one group of things. And your new thing is in that group. Or it's going to say, this new picture looks totally normal. That's fine. Or it looks weird. But what's normal and what's weird, it depends on what you gave it in the beginning. And to give it context, you have to kind of apply some knowledge afterwards. Or you can just say I'm going to detect outliers. I'm going to detect weird things that don't look like my original data. So that's what unsupervised learning will give to you. And in ClearCut, we have an example of doing supervised learning with random forests and unsupervised learning with isolation forests. So I think one of the reasons you're hearing a lot about machine learning nowadays is there's been a couple of, I would say, breakthroughs in machine learning that have really improved the performance of the algorithms by an order of magnitude over what they were for a long time. So that in the case of random forests, they started solving problems at a level 10 to 20% better in terms of how often it got things right than they had been for a period of maybe 10 to 15 years. So it was a really exciting time, maybe 5-10 years ago, when these things came out. Deep learning came out. That also had a huge improvement in their performance. So you saw a big leap in the capabilities of these algorithms. And along with that, they kind of moved out of the academic realm. And a whole bunch of people got together and started writing libraries to do these things for sort of non-practitioners. And that's kind of what we're using. So we'll talk a little bit about what these algorithms are, what they're good at. So we've chosen to use it as an example, random forests. And that's a case of supervised learning. All right? So again, supervised learning. So you have a population of things, 2 types of things. This projector is kind of bad. I don't know if you can see it, but some of these things are blue up in here. Some of them are orange down in here. and there's a whole bunch of gray dots. We don't know what those are. So we have label data. We know what the blue things are. You really can't see it unless you squint. You know what the orange things are. And you have a whole bunch of gray things. You don't know what they are. So what we want to do is pass this to the machine, and the machine is going to find a function that separates these things. And in this case, I don't know, can you even see this line here? There's a line right here. No, you can't really see that. So it's going to come up with a function that says, okay, there's a line here. Everything to the upper right of this line is blue. Everything to the bottom left of this line is orange. So in this very simple case, it's easy to say, okay, that everything that's blue, most of the things that are blue are up here, most of the things that are orange are down here. We can easily sort of draw a line between them. And that would be a very simple classification algorithm that sort of tries to make the maximum separation between these two sets. And there are algorithms that do things like this. So in this case, you would want to optimize something, right? We usually call this a loss function, but we might want to optimize how many things do we get wrong, or we can optimize how far away. We want to be as far from the line as possible when we know things about the labels. So none of these are going to be perfect, almost never. And you can't see it, but even with this line here, maybe we have a blue one on the wrong side or an orange one on the wrong side. So those will be your your false positives or false negatives. But how close can we get to being perfect, right? It might not be a line. So there are lots of different ways to draw these, to create this function, right? It can be, circle, it can be a squiggly line. And I actually retweeted something the other day that shows the way different algorithms will separate these things, separate different classes of things based on where they are. A line's great if everything's sort of on one side or the other, but what if we were one group's in the middle and then the other group forms a donut around it? A line would really be bad in that case, right? So, and what you want to do is try to create a general algorithm that will handle all cases. That's really hard, right? So a couple of algorithms like this one came out that do pretty well in most cases. So this is random forests, and one of the things is so Python has a really good implementation of random forests in a toolkit called scikit-learn. I'll talk about that a little bit. So kind of the sequence here is you want to identify positive or negative sample data sets. These are your labeled data sets. You always have to clean and normalize the data. Every data scientist here knows that, right? So you have to partition the data into training and testing data sets. So what you do is you take your labeled data, you usually split it up into two pieces. One piece is going to be the set that you train on, and you take an independent set that you want to hold back and to check to make sure that your algorithm is working correctly. You train the model using the software. Then you test the model on your holdback set and see how well it does. Right? You record how many times it gets things right, how many times it gets things wrong. And then you see how good that is, and then maybe drink a beer after that. So how does the training work, right? In particular, how does a random forest do things? So a random forest is going to create a bunch of these things called decision trees. So we drew a line before. That's maybe deciding what y, m, x, and b are. A decision tree works by taking your set, picking one factor out of that set, one column of data, and asking which column of data is the most predictive for your answer. It knows the answers for this set, so it can figure this out. So it says, okay, this is sort of the Titanic data, right? And you're trying to determine if a passenger lived or died. It's a little bit morbid, but so the first predictor is is this person a man or a woman? So if the person is not a man, then odds are they survived in the Titanic's case, right? So you can kind of split it along these lines. So that's sort of taking one column and splitting it in one place. You split it in the place that's sort of most predictive. Then you take another column that's the next most predictive. So is that person older than 9 or younger than 9? So if they're older than 9, they probably died. And you keep doing this until you reach a point at which this whole tree is predictive enough. Now, this is part of the things that, how do you determine that? You don't really care. So the problem here is that it might look at things that are important in your test set, but not important in the real world or overall. Right? Your test set might be biased. And you sort of go down you go down a path by picking this column and saying, I want to look at, is it male or female first? That sort of biases the rest of the data set, and you can overfit. And what does that mean? That means it's creating a tree that works really well in this tiny set of data, but then when you try to apply it to another set of data, it fails miserably. So what does random forest do? So what you do with a random forest is you take your training set, you take a random subsample of that set, and you take a random subsample of the columns in that set. And that is your little mini training set. And you make a single tree out of that mini training set. And you do that like 100 times. You get 100 trees. And to do a classification, you ask all 100 trees what the answer is, and then you can take a vote or you take the average, depending on if it's numeric or a yes or no question. And it's a simple idea, but it turns out this works really well, and it avoids overfitting and has a bunch of other nice properties, right? So great, it won a lot of contests, it did a lot of great things. They put it in scikit-learn, and now you can create one with one line in Python. And we'll show that to you. All right, so, say we have a bunch of brologs, right? Let's label them. No, that sounds really terrible, right? So there's other things that we can do if we don't want to sit down and label 1,000 lines, right? Is this malware or not? I don't want to do that. One thing you can do is you can use unsupervised learning. So in this case, we're going to do outlier detection. You can do clustering. Clustering is show me the groupings of this data. And this data, it's really clear. There's no colors in this data, so you're not missing anything. But you can say, oh yeah, there's 2 clusters here. Humans are really good at this in certain circumstances. Machines are not as good. For example, you can tell there's 2 clusters here. Even just saying there's 2 here, that's a pretty big deal for a machine. But another related thing is saying, okay, we have this data. Which points are weird? Which points don't look normal, right? In this case, maybe these are normal, maybe these are normal. But this guy over here, he's weird. He doesn't look like the others, right? So this is called outlier detection. It's a sort of subset of unsupervised learning. And you can also pretend that outlier detection is a classifier. You can say, okay, everything that's normal you label as 0, class 0. Everything that's abnormal is class 1, or abnormal class. So you have a classifier, right? Boom. So there's lots of ways you can do outlier detection on data. We're going to talk about one of them, and one that I think is pretty exciting. But other ones are you can say, you can compute all the interpoint distances. So you take this point right here, and you say, how far is it to all my neighbors, right? And it's kind of far on average. You take this point here, how far is it to all my neighbors? Or just maybe the k nearest neighbors. It's not as far. So this guy is probably an inlier. This guy is probably an outlier because its average distance to its k nearest neighbors is high. There's a kind of a problem with that in big data, right? First, you have to compute the k nearest neighbors. That's not easy. And then you have to compute the distance to all those k guys. That's not easy either in a lot of cases. So these are called distance-based methods. They're sort of angle-based methods where you can say, what's the angle spread amongst all my neighbors? So if you're on Mars or Earth, what's the angle to all the planets? It's going to be kind of high. They're all over the sky. But if you're on Pluto over here, the angle to all the planets is narrow because you're an outlier. Again, you have to find the angle to all your neighbors. So these are n-squared operations, right? Because you have to compute it for each pair. It's bad. You don't want to do that. So there's these new isolation-based methods that came out a couple years ago. So what is this? You pick, it's sort of like iForest. I mean, it's sort of like random forest. They both have forest in the name, right? So this is isolation forest. But they're sort of qualitatively different. What you do is you can't really see anything here, right? You take a blank screen. Well, anyway, so you take your data. What you do is you pick one random dimension. Like you say, okay, x. Like this is two-dimensional, x, y. You pick a random dimension, x, this time. Maybe y next time. You pick a random point between the max and the min. So you have to know the maximum and the minimum for each one of your dimensions. That's not a big deal. That's a one-pass algorithm, right? O of n. You pick a random point in there, and you split your data set into two data sets, whether or not it's on the left or the right of that, or if it's above or below it for y, right? Okay, so it's split into two sets. Well, this is forming a node with the tree, right? A binary tree. These guys are on the left, these guys are on the right. So you do this recursively on every node. Every node, you pick a random dimension, you pick a random spot, and then you split. And then you say things that are split off into single node. So if you have a single point in your node left, there's nobody else left in that node. If that's close to the root, you're an outlier. If that's far away from the root, you're an inlier. And why is that? It's because the closer you are to like your buddies here, the more times it's going to take your splits to like split you off, right? And sort of there's bias in this too, so and it's randomness, right? You could get unlucky. So you do it like 50 times, and then you combine the results just like random forest. What's so great about this, right? It's O of n, right? So you just have to pick a random spot and then sort things according to, split things according to that split. That's just O of n, right? And the tree is usually like log n high, so it's like O of n log n. But you don't have to do any comparisons between all pairs of things. And it turns out that, it's kind of the same thing here. But it turns out that this algorithm works really well. It works better than any other outlier detection if your data is like totally numeric. So again, identify positive and negative sample data sets. If you have it, we said this is unsupervised, but if you know that certain things are outliers, you can kind of hold back a set, train your data again, and then check it on the set that you held back. Again, saying like class 0 is the inlier, class 1 is the outlier. So this procedure, right, is pretty much the same. And we have a second beer at the end, right? So that's good. So you'll notice, like with a lot of these machine learning algorithms, you're always going to follow the same procedure, right? The algorithm is different, step 5, training the model, but the procedure is the same. So the scikit-learn guys noticed this. I mean, a lot of people noticed it. So what they did was they created a library where the procedure, the gists, all that code is the same, but just like the creation of the classifier is different, but all the APIs for that classifier are the same. So, these are two completely different types of learning, right? Random forests and isolation forests. They're on different branches of machine learning, supervised learning, unsupervised. But you create the variable the same way, a similar way. You create it with a set of, you create it with its hyperparameters, essentially, which is like the number of trees and stuff like that. That's different. Random forest, you have to have a set of answers, right? You have to have your supervised. How do you go back? You have to have your supervised set. But the way that you do fitting, this is making the model, that's exactly the same code. It's literally copied. And the way that you test predictions on it is exactly the same. That code's literally copied. So all you have to do if you're trying to test different things out is just change the way it's created. And maybe, make a test set also. So you can reuse this analysis script with nearly no change, and you can play with the parameters and find the algorithm that best fits your problem with not knowing how any of these things work really. You don't have to. And these things are all optimized underneath. They use best class algorithms, et cetera, et cetera. So it's like the grep of machine learning here, right? You just type grep, just type random forest, you don't care. And it'll do the things that you need it to do. So David's going to give a demo, I think. A paper demo.
All right. I gotta say, first of all, who's convinced after seeing the 3 or 4 lines of Python code that our general thesis is correct, that you could actually write 3 or 4 lines of Python code? Anybody? Hands up. Okay, we got some hands. We got lots of hands. That's good. I had to say, one of the interesting things about working, I'm not with Squirrel's data science team, but I work with Chris a lot, is we get in these conversations where he's like, yeah, our data set has something like 34 dimensions in it. And I'm like, 34 dimensions? I am in a Doctor Who story. That is awesome. So yeah, this part of the presentation, I just want to walk through a little bit about how I prepared a demo, and then we're going to give a screenshot demo. It's a screenshot demo. This is all terminal text, so it's really easy, but the training times and things take a little bit too long to really comfortably fit into a presentation. So fortunately, I think you can mostly read this. This is a little bit of a diagram about how I prepared the data for this demo. So this demo is about random forests. Show of hands, who remembers? Random forests, supervised or not? Supervised. Yes, we're paying attention, Chris. Good job. So that means we need labeled training data. I need, and our problem is to just try to find things that are indicative of malware requests in our Office Sensors Bro HTTP logs. Basically, I want to know if we've got some malware calling home. I'm not as concerned about what kind of malware it is or anything like that, although there are certainly techniques you can do to extend our binary classification, yes or no, good or bad, malicious or benign, into more complicated things like this is Dridex, this is Locky, this is whatever. We're not trying to do that. I just want to know, do I think that this looks like it might be malware or not? I have 100,000 or 200,000 log entries a day. Don't feel like spending all that time reading it, so I want to reduce it down. Let the machine do something for me. So, and we're doing random forest supervised learning, so I need 2 data sets, right? I need a set of confirmed malware HTTP logs, and I need a set of non-malware benign HTTP logs. I did not really feel like going through and manually labeling a bunch of things from our Office sensors. So what I did instead was I looked for a corpus of HTTP traffic that I knew was super likely, maybe not 100% likely, but super likely to be malicious. So I went to a couple websites, especially on the internet, so malwaretrafficanalysis.net and ContagioDump. Both provide packet captures for malware samples. And that's pretty much mostly all they provide. They don't provide benign samples unless it's by accident sometimes. So I can take that, run all the PCAPs through Bro, and retrieve a corpus of largely malicious network transactions. There's a few things in there that I tried to do a best effort to clean out, things like connectivity checking to Google or CNN or someplace like that, right? Obviously associated with malware, but not itself a malicious kind of command and control. I won't claim that I got everything out because I think that I ended up with something like 25 or 35,000 entries in that corpus, and I didn't review all of them. So there may still be some in there, but my hope is they're statistically insignificant. I tried my best to get the most obvious ones out. So I basically said, everything that's left in this file of combined stuff is the bad corpus. And by the way, this bad corpus is checked in to GitHub. So you don't have to do this yourself necessarily just to try it out. The second thing I need is my own benign corpus. So by virtue of the fact that I look at our network security monitoring data, I feel like we have a fairly clean office network. So again, instead of looking at 200,000 things for the day and saying, do I think this is malware or not, I actually said the vast majority of our traffic is benign. I'm just going to assume everything in here is benign. And if there's a few things that might not be, again, statistically insignificant, I hope. So we just labeled that benign traffic. And all we did was we combined that into one big data set where more or less every row had the benign or malicious tag on it. And then I took 80% of it for the training data. I reserved 20% for that test data. That's this part right here. And you can see I got the training and test. Then we had to do a little bit of feature extraction. This is built into the code. The idea here is that computers are great at computing against numerics, not so good at computing against text strings. So we had to find a way to convert, especially the text strings, into numbers. There's three things that we did, mostly. Straight up, some of the things are numbers, and they're legitimately numbers, like this thing, the number of bytes transferred or something like that, right? Some things are numbers, but they're not really numbers. They're lying. HTTP response codes, you think they're numeric, but let me tell you, they're enumerated data types. Because there's no sensible logic that you can say a 404 is greater than a 200. Or you can't say 300 plus 200 is a 500. It just doesn't work. They're enumerated data types, even though they look like numbers. So we had to convert them into something that you could do computations on. But more interesting are the strings in those fields. So things like user agents, the URLs, the list of if there were HTTP key value parameters or anything like that that was a straight up string, we had to convert those. We used two methods primarily. I won't go into them too much detail because I want to save some time here, but we have the bag of words method, which basically said we count all the words, delimited by white space or some kind of word delimiter. And we say how many times you had any of these words in your string. So if you had a typical user agent, Mozilla occurs pretty often, because most of them claim to be some kind of Mozilla thingy, right? Or WebKit or something like that. And you might have a column that says, was Mozilla in here? Yes, 1, right? Did it have WebKit? No, 0. We also did this thing, same kind of thing, for what they call the bag of n-grams. So an n-gram is just a subset of a string, at least 2, right? Or sometimes 3, 4, 5, could be as long as you want. But we computed some that said, show me these combinations of letters and how many of these were in there. So we had, it's probably hard to see, but the text, the quick brown fox, if you have like a 4-gram or a 5-gram, I think is what they're using. So let's say you have a 4-gram THE space. Did you find THE space in your string? Yes. So basically you compute all the possible n-grams and you record how many of each one you saw in each string, and it becomes a vector, a bit vector that you can actually start doing computations on. So if that sounds complex, it is, but fortunately I didn't have to do that. That was him. And all those things are built in now to ClearCut, so you don't have to do them either. You can just use them. Oh my gosh, you guys cannot see the demos at all. That's fantastic. That's going to make the rest of this go really quick. I'm gonna try and see if this helps at all. No. I don't know.
I feel like I invert this.
I was just going to see if I can maybe move this. Maybe you'll be able to see it better in here.
Start presentation.
Yeah, let's see. No. And I can't even read it. Yeah. I don't know if this will actually work, but we'll try it. Okay. Yeah, it doesn't all fit on here, though, does it? I can't see this. Is this view?
No, it's in the...
Oh, up here. Can't read it. Is it this one, right? Down here somewhere.
One more.
Zoom. Whoops.
Oh, yeah, you can...
Hold on. Let's try this.
Command minus.
Yeah.
Click on the slides.
Yeah, command minus should, yes.
There, we're getting closer. Okay, that's good enough, I think. Woo! All right.
Maybe plus it up a little.
You don't need to do it. All right, let's see if we can do this. So this is just an example. First of all, I'm running the training script. It comes in two scripts, train flows underscore RF for random forests and train flows underscore like IF if you're going to use the iForests. And that's because even though these are mostly the same scripts, just a little bit tiny difference. We could have combined them, but we're lazy. And this is pretty much what you say. You say, well, I'm going to run the train flows. I'm going to give it the -O, the malicious data, and then I'm going to give it the benign data. So just, I'm naming two files, right? And it says, okay, yep, I'm reading it. I'm reading it. And now I'm going to make those the vectorizers. The vectorizers are the bag of words, a bag of n-grams. They're converting the text into the vectors. They're creating the features and changing them into numbers. And basically, and it sits here for a while doing that, and then it sits here for a while doing training. And then it outputs this. Skip all this stuff. So here what we have is a matrix where we say, we said it was malicious. The computer predicted that it was malicious after the training. What is this? 20? I can't read it. Some large number of times, right? It got it right almost all the time. We said it was malicious. The computer said it was not malicious, only like 15% or whatever this says. So it made some errors, but not very many. Again, we said it was benign, and the computer agreed it was benign. The computer said it was malicious a few times. So it got a few of those kind of errors as well. But most of the times, it could have been, right? But most of the times, when we said it was benign, it was really benign. So just looking at that matrix, we think we did a pretty good job. We got mostly the correct answers. We got a small amount of either false positives or false negatives. Now, one of the things that you do here is you go through this process a number of times until you are satisfied with the answers. I didn't show you this. When you're creating your own log files and adapting it to your own log files, you need to figure out if you are in the ballpark of something good or not. It's nice to be able to see this to kind of get details, but it's hard to compare it, a whole matrix, to something that you did before and see if you're improving or not. So what we also have at the bottom is this F1 score, which is kind of a standard score of a model that basically takes the ratios of all this stuff here and converts it into one number. In general, like a ballpark heuristic, if your F1 score is above 0.9, you're good. You're doing pretty good. Ours, 0.998, I think that says, suspiciously a little bit high, but pretty good. I'll show you why it's suspicious in a second. Now, here's a bonus on the training script. If you run it with the -V, it can tell you what it thought the most influential features were. It doesn't say for this feature, this is the most influential benign feature or the most influential malicious feature. It just says these features had the biggest impact on the training. And you can see the biggest ones up here are like Mac OS, OS X. Yeah, because I made a mistake, which I elected to keep in here so that you won't make the same mistake. I went out onto the internet and got primarily Windows malware, and I have a primarily Mac place. So basically my model is more or less just telling me, if you have a Mac, you're good. That's not entirely true, because you can see there's some other things in here, like the number of dots that it had it found in the domain names you're going to and things like that. So like if you're going to an IP address, you have a lot more dots, right? But it's heavily biased for Macs being safe, because we didn't have a lot of malicious Mac stuff. So when you're going out there, if you are like a typical Windows systems all around your enterprise, most of what you find on the internet is going to be fine for you, right? If you're not, you might have to do something a little bit better with your data than I did. And then now the model is trained, and by default it's saved. There's options you can say where to save it, what to name it, and whatever. But it's basically, we took the default, so it's saved in the current directory, and it's ready for you to go. And then you can use that trained model on your production log files. So here's again, analyze flows. No matter whether you're using random forest or iForest or whatever, it uses the same analysis, because we're just dropping in that model that we trained into the APIs. So they're the same. And you just give it a file of log files, bro HTTP log files. And notice what it said. It said I have something like 200 and something things for the person to review out of, like, I think it says 180-some thousand. So I ended up reviewing like 0.17 of the log files. That's not too bad, because now we're definitely getting back into the part where we're saying the human can actually do that part. This was the cyborgism part, right? We let the computer learn what to look for. We let the computer look for it, and if it found something that it thought we needed to look at, there it is. And it drastically reduced the number of log files. And it basically eliminated virtually all of them. So we didn't have to worry about it. And the ones that are left here, we can look at each one of these individually. Also a bonus on this one's the same -v feature that you can use to show what it found for each one. Again, it won't tell you if the most influential feature said it was benign or not, but it was the most influential features for that individual log file entry. So you'll get one of these. It takes a long time to do this, by the way, this extra calculations, but sometimes it's kind of cool right at the beginning when you're getting used to it and you need to see if you have some trust in your model. You can throw that up there and see what's going on, really. So now let's talk briefly about adapting this to the other log sources. There's basically three things that you might want to do. And since I can't read it, I might ask Chris to help, since he did this part. Can you read this? There's three things. And if you want to get the slides and find out what they are, follow us on Twitter. It basically, it's just saying, yeah, it'll be up there in a minute. And it's basically just saying, here's the three places in the code that you need to check out. And it's what you need to change the log file input. So if you're not reading bro HTTP logs, you might have to change the format of the CSV reader. In the flow enhancer, you might have to change the columns that you're featureizing, converting into numerics. And then in the generator, there's one of the helper utilities that comes with it, where you may have to change some of the things a little bit to make the compute the correct bag of words or bag of n-grams on the right fields. But in other words, most of the things you have to do are straight up data-oriented and not machine learning internals. And so for the wrap-up, so there's 4 key takeaways from today, right? The first is pandas and scikit-learn, especially the scikit-learn, they're really active Python projects. And they are so well documented on the internet. You can buy Riley books or whatever. They have done a great job of bringing these kind of data science, data analysis tools into people like myself who are not really data scientists, and let us being able to use them, just having, in my case, just a superficial understanding of the strengths and weaknesses, so I can maybe choose the best algorithm, but I don't have to know exactly how it works, and I don't have to know exactly how to program it, because it's already done. So security technologists, we can start using these things in our daily work as kind of black or gray-ish boxes. It's to the point now where if you have a problem in front of you with a pile of data and you don't know how to find the pieces that you want, you could conceivably see, is this something that we could use either structured or supervised or unsupervised machine learning to do, and just write a thing. Implementing the algorithms is not something that you have to do. The machine learning part is really the easiest part. The hardest part is getting that data flow pipeline that Chris was talking about set up correctly so that you get the right data, the right features, and et cetera. It's straight up data programming. It's not data science. So it's easy to do. It might take a little bit of practice, but it is not magic. And then we have, on the next slide, I'll show you the URL that you probably can't read for clear-cut, on GitHub. So our Twitter handles, so I'm just at David J. Bianco. This is underscore secret stash underscore. And I promise I'll put the relevant links on our Twitter feeds so that you don't have to worry about whether you can read them online or here or not. But if you go to my GitHub for David J. Bianco, you'll also see the clear-cut repo that has the sample malicious data and all of the Python code. So with that, do we have any questions? Oh, there was a really quick question.
With regard to isolation force, is that going to be sensitive to the kind of distribution of your data? Like a lot of data we deal with is going to be long-tail distributions. Like if you look at histograms of websites you go to, you're going to see a long-tail distribution there. Will an isolation force be kind of sensitive to that? Is it going to work well for that?
So they've done experiments, and it seems like the distribution doesn't matter that much for isolation forest, which is one of the advantages of using that technique. In some cases, like if you do have a long tail, it's kind of like what is an outlier in that case, right? Like if you have a Zipf distribution or something like that, something is quote normal, but it is unusual, right? It doesn't happen often. So yeah, I think in some cases you will get false positives when things are actually normal, but are just out on the long tail. But that could be considered an outlier in some ways anyway. But yeah, so there are considerations, of course, with distribution of data. But they've shown that iForests are good at lots of different distributions. And you can look at their paper. There's also a paper just last year in, I forget which conference, I can post it, but it was comparing iForests to other methods, the other methods I was talking about, and iForests were like the clear winner. Yep.
So I guess the underlying hypothesis is that outliers are bad, right? Does that
well, interesting, but maybe not bad all the time, right? So I see that we are kind of eating into the setup time for the next presentation. So if you have any questions, Chris and I will be hanging around a little bit after the talk, and you can ask us in person. But otherwise, thank you very much for attending.